So I definitely didn't just waste 30 seconds talking about inner or ear disorders. All right. So before we even get into actual equilibrium, let's just review the basic ratio, the basic concepts of molarity. I still have a couple people who botch molarity calculations and mistakenly switch moles and molarity. You can't just swap moles and molarity. They are not the same thing. Molarity is how the moles are distributed, how much space or volume they're distributed over. Let's make it real clear though, it's per liter, not per milliliter. So if you have 25 milliliters of something that is 2 molar, and you want to know how many moles that is, number one, it's not 2 moles. You can't just go 2. You have to do 2 seconds worth of math. Number one, let's just throw this into the calculator, the equation. 2 molar equals 0.025 liters over X moles. So you have to cross multiply, and that would be 0.05 moles. I do that math right? Yeah. So you multiply the 0.025 over, and that is 0.050 moles. So those moles are spread out over that volume. Remember, the switch between milliliters and liters is a difference of 1,000, so we're moving the decimal place 3 spots. Lastly, you could leave it in milliliters. What? Barbarian. If you leave it in milliliters, though, you don't get moles, you get millimoles, which is fine. It's okay. You're allowed to work in millimoles. People often work in millimoles when they're super tiny. Like this would have been 50 millimoles. Cool? And people often do that when they get to decimal answers because honestly, who has trouble visualizing the number 0.2 in their head, but they are great with the number 20? No one? Okay. Like your lack of head movement or any sort of gestures was really impressive. I can do those equally. All right. So what are we going to talk about today? We're talking about equilibrium. And when you discuss equilibrium in regular chemistry or intro chemistry, they really focus on the idea of rate and rate. And they say that the forward reaction rate is equal to the reverse reaction rate. And they say this like a dozen times. And then they spend how much time discussing rate, though? Like 0, which is kind of amusing. Where we just spent a whole lot of time discussing rate, didn't we? So let's write the rate law for the forward reaction. The rate law for that forward reaction would be rate equals some value of K, hydrogen's value, times iodine's value, right? Would that be the forward reaction rate? Right? The forward reaction would be hydrogen times iodine, and a K would equal the rate. Do you mind if I put a little F here? What do you think that F stands for? Forward. All right. Now, let's write the reverse reaction rate. The reverse reaction rate, I'm going to put a tiny r there for reverse, is equal to K HI squared, right? True? So if one student starts off with hydrogen and iodine, boom, reaction starts and it's moving forward, making hydroiodic acid. Another person in a completely different laboratory starts with hydroiodic acid, it's breaking apart, making hydrogen and iodine. Eventually, they both come to equilibrium. What does that mean again? That the rates are equal. If this rate equals that rate, what is also true by like some math property I can't remember the name of? If this RATE is equal to that RATE, this value here equals this value here, doesn't it? Those become equal to each other. So what we would have KH2 times I2 equals KHI squared, wouldn't we? What does K stand for? Constant. So we have a constant for the forward reaction and a constant for the reverse reaction. And eventually we start moving constants around and we get to what you did study in regular chemistry was writing a rate expression, or I'm sorry, an equilibrium expression. And you would say, the rate constant is equal to the products over the reactants, and it would be HI squared over H2 times I2. You would set up expressions. But the reason this K was there, it was actually a constant divided by a constant, which should be a new constant. All right? So it was actually the idea of rate merged into a new super equation. All right, let's read this other stuff. So dynamic equilibrium is when the reaction is reversible, can go both directions. Reactions that aren't reversible don't usually work like this. We might talk about a couple of them. What is true about the initial forward versus reverse reactions? Usually we have all reactants and no products, and the reaction's only going one direction for a little while, so the reverse reaction doesn't even exist. At equilibrium, they're equal rates. Why does equilibrium occur? Some of the compounds formed can be unstable or semi-stable, so they'll form and break and form and break. And they just don't have very strong bonds to themselves. Or maybe the energy of the entire system is such that all of the molecules are completely unstable at 7,000 bajillion jillion kelvins, like in my basement. So everything just moves around and they keep colliding and breaking and forming molecules that are unstable and then breaking back down. What are some factors? We're going to talk about concentration, which is something I also hope to have from you today. That was you couldn't hear the laughter at home, but there was some. The state of matter, solid, liquid, gas, aqueous. We're not going to get into plasma or any of that other weird stuff like the Bose-Einstein condensate. Temperature, or the nature of the chemicals. I wonder what that means. So some giant molecules can have really odd components, like if you get into like octane and things like that, where they're big, long organic compounds. All right, click, click. Remove that. So I want to point out real quickly, this equation is on the equation sheet. It's a pretty boring equation, isn't it? This equation is on the equation sheet also. So those two are on there. So if you were ever stumped as to whether the products go on the top or the bottom, they've given a variable version of an equation, and then they're like, look, they're on the top, they're on the bottom, do it that way. All right? How many plus signs do you see in the equilibrium constant expression here? None, because it's all multiplying and dividing, right? So even though you see this plus sign here, it ain't there. No, it's not. That's multiplying. I used ain't. I'm sorry. So what we will, beginner level equilibrium, the beginner level here, is we'll just take reactions like this hydrogen and iodine and write them as expressions with the products on the top, the reactants on the bottom. What happens to the coefficients? These coefficients are the order for that part, right? What is the order for hydrogen? 1. So it's a 1, and the iodine's a 1 also, and they're being multiplied. I accidentally already have all of the answers revealed for the next question. Take a gander at that for a second. I'm going to pause here in the classroom while you... Okay, that was funny. So I have a good question out there. All of these are in brackets. Brackets mean molarity. And so what a lot of times you'll see is an adorable little C here next to the K, which means that we're talking about the concentration or molarity. It is not, for lack of a better word, constantly written down. That C is not always written down. But if someone doesn't have a letter there, then people always assume they're talking about molarity. We're going to talk about equilibrium constants, bless you, for acids. We're going to talk about equilibrium constants for bases, which will have A's and B's. You guess which one goes on which. We're going to have equilibrium constants for water. Guess what letter represents water? W, right? And we'll have equilibrium constants for pressure, which they'll throw a P in there. If I can remember the sign language for P, I'd make it. And what's another one? Ooh, SP. Anyone know SP? No, not special. It is actually about how soluble the products are. It's a solubility thing, which we're going to get into a bit later Actually, that's in part 2. The part 2 video has solubility product constants and things like that, which doesn't mean anything to you right now, which is why you're going to watch video 2. All right. That goes for you at home. All right. Click. So now we're taking it to the next level. The next level? Nice. All right. Neville, easily the best character in all of Harry Potter, hands down. The most character development. We can have that conversation a different day when I'm not recording nonsense. So here I've got the expression, right? I pulled the expression based off the reaction, and then I plugged the values in. Most common mistakes. Morgan's got everything plugged in right. But she forgets that there was a little adorable 2 there. What should she be doing to that 1.29 in her calculator? I can't tell you how often people have everything plugged in right and then typed wrong. And then I have to check and try to figure out where they got their weird answer from. I have also circled the at 25 degrees Celsius. That must be for some reason. I don't know if you remember we did reaction rates. You probably do. It was last week. And we said that this reaction only works at this speed and concentration if the temperature is whatever it is today. And if you change the temperature, things change, right? Well, since equilibrium constants are really a ratio of constants, this constant, 710, is only true if the temperature is? If we change it from 25 to like 72? What did that happen? Became Elmer Fudd. If we change the temperature to anything other than 25 degrees Celsius, that constant will change. We will discuss how to predict whether it goes up or down, depending on whether or not the reaction's endo or exothermic. But let's hold that off till later. Number 3, we've just given Peter this information. He already knows the constant. He knows the hydrogen value. He knows the iodine value. He's trying to figure out how many highs are hiding in there. He needs to make sure that he doesn't just cross multiply. He needs to take a square root. Right? Because that's actually like x squared. And if he doesn't take a square root, then he's got the answer in terms of x squared. And that's a pretty common error also. As people get real close to the answer, they plug everything in, and they're like, and the answer is 17 point whatever that would be before you take the square root. So, all right. Now, secondary question. You're in AP Chemistry. This is too easy. I don't think I stuttered. You're in AP Chemistry. This is too easy. So this would not probably be the end of the question. The next part of the question would be like, so Peter, if the solution is, if the bottle is 4 liters big, how many moles of hydroiodic acid are bouncing around inside your bottle? And if you have the molarity and you have the volume, can you find the moles? Yes, that's what we started off, right? Could you find the grams? Can you change moles into grams? Those other questions might actually be what the question is. It might not ever say, figure out the molarity. It might give you this information and say, it's a 4-liter bottle. How many moles? So you have to go through, now multiply by 4 to get to moles, right? And so that's really the sort of question we're going to see. I agree with that slamming the door. It's really angry. Is that you always have like 2-step problems. Really, we're getting to a lot of those where you have this information, you can do stuff with it, but that doesn't get you to the answer. You have to do more with it. So kind of seeing the options. Hey, what if we wrote the reaction backwards? Instead of the products on the right side, we wrote everything backwards. That would be like flipping everything over, right? Because if A is making B, then we would have said K equals B over A. True? Yeah. If, however, the reaction's written reverse, wouldn't we say it this way? Someone sneaking in the door? No? Oh, I missed that. It was very sneaky. I had my back turned. So this is the inverse of that, isn't it? They're the inverses of each other. So if someone has the equilibrium constant, but then they write the reaction backwards, they really should do what to the equilibrium constant? 1 over. So up here somewhere it says that they've reversed the reaction. Reverse of the original. But that's the only thing other than changing the temperature that would give you a different answer. If Rheem doubles the amount of one of the compounds, the reaction's going to react, reach equilibrium. It's still going to be 710, right? But if you're working the reaction from the reverse perspective, then the equilibrium constant's really the inverse of what you were expecting. Oh, wait, one last thing. The equilibrium constant, like 710, implies what you have more of and what you have less of. 710 products for every one reactant. It's a ratio of products to reactants. And look at the values in this question. 1.29 as compared to 0.02 and 0.1. True? More on top, less on the bottom. That equilibrium constant hints at that. It's above the value of 1, so therefore there's more on top. If it's below the value of 1, there's probably more on the reactant side, more on the bottom. All right. Equilibrium involving pressure. This equation is given to you where? Yeah, it's on the equation sheet. It looks so much like that other equation in terms of the form. It's still products over reactants. It's just covered in the letter P, isn't it? And the letter P in this case does not represent phosphorus. I had a kid one time go, "Why is phosphorus everywhere?" It's like, what? He was serious, so it hurt me for a minute. This is pressure of whatever element C is. Pressure, pressure, pressure. Lots of under pressure going on in there. So you solve it the exact same way. Here's a reaction. They've got methanol decomposing into carbon monoxide and hydrogen. I set up the expression. K for pressure would be the... I forgot to type the P's in there. Please excuse me. Pressure of CO. Pressure of H2 squared. Pressure of methanol. It's not uncommon for them, Vincent, to just say, hey, set up the expression. Then go on to question B. Yes?
So it says that Kc and Kp can be related. What does it mean by related? Does that mean like they're all proportional or one increases the other?
I just did that in the microphone. So he asked, how is Kc related to Kp? There is an equation that relates the two, which we're not learning, we're not going to use, but it's a weird combination of PV equals nRT and these equations here. And it has, it's like, don't write this down because it's so wrong, all right? But it's like natural log of RT to the change in moles or something like that. It's been a long time since I used that equation. It's actually in your textbook, so feel free to learn it for no reason. But it does allow the two to be equivalent to each other. That's not it. That's going to bother me. I can't quite remember the right equation. But so they are related, but they're not equivalent. So you're right, though. If one thing's increasing, you'd expect maybe the other to increase. Okie dokie. So plug values in. You could solve for Kp. Why is this here? What the heck? What is the pressure total? Blah, 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 blah. That's just kind of me trying to remind you that you used to do things like PV equals nRT all the time, right? Yeah? Pressure equals volume moles. Or maybe Dalton's law, that we can add all the pressures together to get the total. What if I did this, Teddy, right? No. Dang it, and I recorded that. Isabella, what if I hadn't given you this value, but I told you the total, and I told you the other two, could you solve for the missing piece? Yes. How, Matt? Algebra. He could algebra. So if you know these two values and the total, and that's what I'm trying to get at here, again, giving the straight values is a little too easy, right? You're never getting to see those questions on a test. You're getting the, I have to do something to get the values to get to the point. So you have to use a combination of things. So what I might do is Say, here's the total pressure, here's some of the components, figure out the missing components yourself, and then solve for the equilibrium constant. Click, click. Oh, while we're here, look at this amazing balloon. Right? Isn't that a great balloon? What the heck is this balloon about? People often visualize the scenario wrong. Here's how a lot of people visualize it. There's methanol. It makes these, but they're in a separate box. They think like there's elves taking the pieces out of box A and then putting them into box B, but they're not. All of these things, all three chemicals, are in the same container flying around, colliding with each other and the right components. They're all in there together. So if Justin changes the volume, Justin's changed the volume for everything. You got me? All of them. They've all shifted around. They're all getting impacted. It's not like I changed the volume and this box gets smaller. Everything is in the same box. So when you change the volume or you change the pressure, you changed everybody's situation. Okay? Right. Now let's get heterogeneous. First of all, heterogeneous means multiple types involved. So far, all of the examples have been gas, 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 gas. Did you notice that? One person noticed it. Some people don't even. Yeah. Good job. All right. So now we got to talk about how do we deal with solids and liquids. And I'm much better at explaining the solids than I am the liquids. Just be bluntly honest about my abilities. So a solid moves how fast? Here's a solid, right? Cool? I'm going to open it up. There we go. This is I've got a wet nap for you to be like a cleaning thing. Is some of the stuff in here vaporizing off? Right. And it's flying away, right? Now if I trap this inside a bottle or something, oh, am I ever going to get that out? Let's just do that so I can still get it out. All right. Which is moving faster? The gas particles vaporizing off of it or the solid that's sitting there? The gas particles are moving at about 400, I think, and 20 meters per second. 420 meters per second. Almost as fast as Peter on the basketball court. Not quite. It's pretty fast, though. How fast is the solid moving? Really close to zero. It's like vibrating back and forth, but not like flying. So if you were comparing how fast the objects are moving, it's like 0 versus 400. So the one that impacts the reaction speed is the gas, not the solid. So the reaction orders, I've retrieved it. The reaction orders, you replace solids. Solids get written to the 0 power, or 0 order. What happens if anything's to the 0 order? They become ones, right? They become ones. And so this reaction here, calcium carbonate, breaks down into calcium oxide and carbon dioxide. You have two solids and a gas. If you want to reverse this reaction, the primary thing you can do is put in more carbon dioxide. Adding more carbon dioxide will shift it back faster. The calcium oxide doesn't really impact the reaction much. All right? It doesn't really impact its movement, its equilibrium position at all. So we replace the solids both with ones. So in this reaction, the equilibrium constant is equal to the carbon dioxide value. Side story, and I'm just going to pretend with this bottle here. Oh, actually, this is a perfect bottle. This is a, listen, sound effect. There we go. This is a sodium carbonate bottle, and carbonates decompose slowly. If you leave the lid off, not like you're not seeing anything. Don't feel like you're missing anything at home. When you take the lid off, the carbonate that's producing carbon dioxide, what can happen to the carbon dioxide now? It can float away, right? And if it floats away, can the reaction reverse? No. However, If I wanted to reverse the reaction, right now some of that carbonate, the carbon dioxide is floating away, I could drop like a chunk of carbon dioxide in there and then let it all turn into carbon dioxide. After it's all turned into carbon dioxide, then I could seal it. I didn't want to seal it before, the bottle might explode. So the dry ice turns into carbon dioxide, fill the container with CO2 gas, then seal it. Now I've got a lot of CO2 trapped in there, and it might react with some of that oxide and push it backwards to get it back into equilibrium, because there'd be so much extra CO2 in there. That's a very exciting demonstration. So with all of these reactions, if there's a solid, we would just replace them with a 1. If there's a liquid, we also replace them for a 1. I don't have any magic explanation for that other than to say that anytime we see a liquid, it's also 0 order, and they just get replaced with a 1. All right? So solids and liquids, 1s. Honestly, I think water's the only liquid we encounter. Can you think of another liquid? Not something dissolved in water, but another liquid. Like the alcohol family. You could hit a bunch of alcohols, ethanol, methanol, propanol. There you go. You got some liquids there. We don't typically do reactions with them, though. They don't do inorganic reactions. They do combustible reactions and things like that, right? I guess we just did the acetone iodinate, that thing. Yeah, lab. And that was interesting. It was like a single displacement reaction of sorts. But the liquids get replaced with 1s. Okie dokie. So, applications of the equilibrium constant. Right now, a lot of reactions in this room are not at equilibrium. So what's happening if they're not at equilibrium? It's moving that way, right? So, can you drink some of that water for me? Yeah. Thank you. All right. So, the volume of space just changed, right? And so what's going to happen is some of that water is going to vaporize and fill that space that's now available. But for a second there, it's not at equilibrium. What I mean is the rate of vaporization and the rate of condensation weren't equal. Now the space allotment has changed, so it's going to adjust. It's going to re-achieve equilibrium. So chemists love to calculate things. And so what we do is we calculate what's called the reaction quotient. What does quotient mean? Division. So what they're doing is they're still doing products over reactants, but they're just saying it's not at equilibrium. It's not there. We're calculating a value to show that we're not there. And then we compare that value to K and see how far away. So say that Pond's got a reaction, the equilibrium constant is supposed to be 407. You mix all your chemicals together, the reaction's going, you write down some math. After your math, your reaction quotient's 0.2. Is 0.2 anywhere near 407? So your reaction's got a long way to go where the products are being made as the reactants get eaten up to move towards equilibrium. So the book talks about comparing the Q and K. I usually just think it from a math perspective. Let's look at this example down here at the bottom. Super zoom. Let's say that Elijah has an equilibrium constant of 40. He looks at the chemicals he's mixed together. Currently the ratio is 30. I think we all agree that 40 and 30 are not equal. So currently, is Elijah at equilibrium? No. So the reaction is going to move either to make more products or it's going to move to make more reactants. What does he need more of to get to 40? This value has to increase or decrease. It's to increase to get to equilibrium. So if you're going to increase the products or the reactants to make Q larger, going to increase the products. So the reaction needs to shift to the product side. And I don't mean it needs to like it's a human and it needs cheese for breakfast or something like that. I mean, it's not in, no, just me? Okay. It's not in balance, and the reaction tends to move towards the equilibrium constant over time. It might do it in 7 seconds, or it might do it in 20 million years, but it slowly moves towards whatever its equilibrium constant is for that temperature. So it's not currently at 40, so they slowly would see an increase, or maybe quickly, an increase in the products, a decrease in the reactants until we achieve that 40. Okay? What if it was the opposite? What if it was 0.4, but as K was 30? We would need to decrease the products, increase the reactants, it would shift that way. So here's what we have. A bunch of examples of that idea again and again and again. You all playing at home, go ahead and pause the video so you can write down some stuff. Like the... and that's why we bought a cat. So, what? So what's going on here is it's the same reaction the whole time. Believe it or not, I'm not going to ask about this reaction on the test, but the exact same concepts. So this reaction's been tested by a young man named Gus, and he eventually figured out the equilibrium constant was 710. All right? So this reaction eventually reaches equilibrium of 710, assuming the temperature is 25 degrees Celsius. And then comes along Sydney. She mixes all her chemicals together, and then she does some math, and her reaction quotient is 427. Sydney, is 427 equal to 710? No, under every math system it's not. And therefore you're not at equilibrium, are you? So the reaction is going to move one direction or another eventually. You're going to reach equilibrium. Does this value need to increase or increase? It needs to increase, right? So we need more products, and that's what it's saying here. The reaction would shift to the right, making more HI until Q is increased to equal K. B is pretty much the same thing, but in reverse. C is a little bit trickier because you have to plug in the values first to figure out where the heck you are. True? You plug those values in. Last time I checked, Shreyas, is this equal to 710? 0.94? 0.94 is a million miles away from 710, right? So they've got to increase the products radically, decrease the reactants. J plugs her values in for D. Boom, boom, boom. She gets 710. She's accidentally at equilibrium. Which way does the reaction shift? It doesn't. It's going equally in both directions already, right? And so you could test where you are. I like to think of Q as right now and K at some future equilibrium. So you could be before equilibrium or after equilibrium, but you're always on your way to equilibrium until you're there. Yes? Because in reality, her question was, why does it say that there's no change visible? The reaction doesn't stop at equilibrium. It's just the rate forward and the rate backwards balance each other out. And from our super perspective at human size, we're not going to see, hey, we switched around. Hey, we switched around too. And then they're canceling each other out. Right? As if the molecules talk in adorable little voices. All right. Blah, 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 blah. So this is a very mathematical approach for just figuring out which way a reaction might move to reach equilibrium. Quick. All right. Nope, skipping that. I've given you too much time at this point. Okay, I'm going to pause. You guys write this down. We'll come back and explain it in just a second. There is one change here, though. This 15.7 needs to be 47.1 for the math to work. That needs to be 47.1. All right, so we're back. So here's what we're going to do. This question, let's just read it and pretend that rice table thing didn't exist. All right? Because that's how it's going to be on the test, right? It's not like I'm going to go, here's an organizational data table. Please fill it out. I'm going to have a question, and then you're going to have to think about all those things. I'm suggesting you use this method to help you solve the problem. All right, calculate the equilibrium concentrations. By the way, molarity is the standard unit for concentration. If a 5-liter vessel initially contains 47.1 grams of carbon monoxide, 29 grams of oxygen. When equilibrium is achieved, 74% of the oxygen has reacted and been converted into carbon dioxide. And then normally it would not say this. It would just say determine the equilibrium constant or something like that. All right? Say, hey, figure out the equilibrium constant. I'm suggesting anytime there's this complex data and they're asking for a constant or something like that, you create a rice table off in the corner to organize the information because it's a little too complex to work it all out. First things first, equilibrium constants are set up in terms of what units? When you have, it's the products of a reactants, but it's the concentration, right? It's the molarity. So everything in this chart needs to be really in terms of molarity, moles per liter. So what did I do with this 47.1 grams? What did I do with the grams first? Converted it to moles, and then I divided it by how many liters? 5 liters. That's where this 0.336 came from. That was right here. I have it already written on the board. 47 over the molar mass over 5 equals 0.336. That is the initial value moron. Sorry, talking to myself there. This value is the mass divided by the molar mass to convert to moles divided by the volume, and I got my molarity. I did the same thing with the initial amount of oxygen. 29 grams of oxygen divided by the molar mass divided by the volume gives me 0.181 molar for the oxygen. That's where this value came from. All right, let's read that sentence again. Initially, there's carbon monoxide and there's oxygen. How much carbon dioxide, CO2, does it say is in there initially? This and that. Does it mention any carbon dioxide? So is this a safe assumption? 0 is the amount that's in there. Cool? So, can we remove any carbon dioxide from the system? Why can't we remove any carbon dioxide from the system? It doesn't exist, right? So we can't subtract anything from that value. We must be adding to this side, right? We must be adding to that side. We must, as we achieve equilibrium, be subtracting reactant values and adding to the products. We're going to be adding to the products. What we will typically do is use the coefficients as a guide. For every x value, what are you guys talking about? I'm literally telling you that right now. Just listen. I'm literally saying that right now. What we do is we assign x values based off the coefficients. For every quantity of oxygen lost, carbon monoxide would also be lost. But since it's a 2-to-1 ratio, if I lose 3 oxygens, I would have to lose 6 carbon monoxides. True? So we plug x's in there. So that's why I have this purple x here. If I lose x quantity of oxygen, I'd have to lose twice as much carbon monoxide. How much carbon dioxide would I be making in terms of x? I'd be making 2 x values, right? Now we come to the, how can I find x? The next sentence has a huge clue in it. It says, when equilibrium is achieved, 74% of the oxygen has reacted. So is the oxygen still there? No, it's reacted. It's no longer reactant. It's becoming a product. So if we subtract 74% of that value, we'll know how much oxygen is gone. So how did I get this 0.134? I figured out what 74% of the original was. I just did 0.181 times 74%. And that's how much oxygen reacted. 74% of the original reacted. That's how much oxygen I'm losing. In red, it's 0.134. Does that make sense? That you have to read the sentence carefully. Now that we know the amount of oxygen, how did I get the other values? How did I get this 0.268? For every oxygen that's lost, how many carbon monoxides do I have to lose? 2. So if I know this is 0.134, this has to be twice that value, doesn't it? True? So that's what I used those coefficients. That's a mole ratio, isn't it? And I'm applying it to molarity. And molarity is moles per liter, so I can use a mole ratio on molarity to figure out how it would change. If I am losing 0.268, what is the missing value for carbon dioxide here? How much carbon dioxide am I making? Why is that also 0.268? Right. I'm losing 2x. On the other side, I'm making 2x. True? So I'm going from 0 plus 2x. If I already know the value of 2x, I just wrote that as the equilibrium value. Now I can fill in these two missing spots down here, this spot and this spot. I can just do some simple subtraction. I'm going to throw this one to you. Can you subtract 0.336? Subtract that out of 0.336 and tell me that answer. And there you go, Elijah. You have 0.181 minus the 0.134. Tell me how much oxygen is left. Okay? What you got? 0.068 and 0.047. They're both trustworthy young men, so I'm trusting them. So that is how much was lost. I took the initial value, subtracted how much it was changing by out. This is what's left at equilibrium. How do I solve for the constant now? I have the equilibrium values. Yep, plug in the numbers into this the law. So the law for this one would be CO2 squared over CO squared and O2, right? So we plug those numbers in. K would equal 0.268. Don't forget to square it. Over both 0.068 squared and 0.047. I feel like it's a big answer. I can't do that one in my head. Like 1100 or something. What? I don't remember the answer at all. 330. Someone test him and see if you get about 330 also. I would hate if the people at home were doing the math and they're getting 317. I'm like, what? Not. No one. Oh wait, we have someone rapidly typing on his calculator. This is a very dramatic moment here from home. You can feel the tension building. 343. Oh no, oh no. Oh. Maybe I did. We're going to pause while we test the thing. So the mighty Gus was right. K does equal 330 here. So I'm sure after one example you understand that 100%, right? I think we should do another one. Maybe with different values. How about this one? Right? So, where do we start? We read the question. True? What does R stand for? The reaction. So you write down the reaction. You don't need to make perfect squares, okay? None of that stuff. And then you have ICE, initial change equilibrium. And this is about organizing the information that's hidden in a word problem. So take a second, read the equation, read the question, and write down the initial values. Let's call on who have I not talked to yet today. I haven't talked to Sanchali or Pan or Yusra. They're hiding. So I think, Sanchali, what is the initial amount of H2SO3 in that question? All right. Pan, what's the initial amount of hydrogen in that question? And Yusra, what's the initial amount of HSO3 in that question? Also 0. All right. There can only be plus X on one side and minus X on the other side. It's not always products and reactants. However, do we all agree you can't have a negative amount of something, right? Let's try this out. Asha, give me your dog. Do you have your dog with you? Where's your dog? You can't give it to me, can you? You can't lose something you don't currently have. True? So you can't subtract from these sides, can you? The only thing that can be happening on this side is addition. On this side, though, we're going to be losing stuff. We're going to be losing reactants and making products. Because we can't subtract from 0. I know in your calculator you can get negative answers, but you can't get negative answers in actual matter. All right. So I'm going to throw X values in there. If it's 2x, 1x, 3x, that's totally dependent on the coefficient. What are the coefficients across the board? So they're all x, x, x. True? All right. Now, let's keep reading. Yusra, what other piece of information have we not used in this question that's a little bit odd? The pH. The pH equals 1.98. We haven't done pH in probably a year, not for real like you did it in Chem, but you haven't seen it in a while. So I'm going to write some equations that are on the I'm going to write an equation that's on the equation sheet. pH equals the negative log of hydrogen. That's the equation on the equation sheet, which is going to be helpful to us right now. So this 1.98 is going to help us find how much hydrogen is there. It is not the answer, though. I don't want someone to write 1.98 in that box, because it's not the amount of hydrogen, it's the pH. We know this value. We know, come on, Red. We know this value, not this value. True? So what do we know? We know 1.98 equals the negative log of hydrogen. But we have to reverse the log process, which those of you who have calculator, Reem, you have a calculator. What is on the log button other than the word log? 10 to the, right? If we raise both sides to the 10 to the power, we're going to get rid of the log. There's one other thing we need to get rid of, and it's that negative sign. So we go 10 to the negative. I'm going to switch colors here. And if we do another negative here, it turns that into a positive. But what? If pH was somehow natural log, yes, but it's not natural log, it's log. Yeah, the log system is base 10, so every time you change by a factor of 10, you change by a pH of 1. Yeah, it's an exponential system. And the whole reason that negative thing is going on in there is people, not people like you. Normal people hate negative values. Like if I say what's negative 2 plus negative 5, a lot of people are like, shut up. Right? But you guys are pretty freaking good at math, otherwise you wouldn't even cross the threshold, right? Like if I say what's negative 2 and negative 2 multiplied together, most people are like, 4. Haha. Multiplied together. Oh, she's slow on that one. So in this case, though, this pH actually tells us the molarity. So Reem, can you do 10 to the negative 1.98 in your calculator for us? And essentially 1.98 is really close to what number? 2, isn't it? So I'm expecting her to give me an answer that's like 0.0 something something. What you got? 104. And the reason I was expecting that is this is 1.04 times 10 to the negative 2, isn't it? 10 to the negative almost 2, 10 to the negative 2. When you plug that pH into the equation, you're putting it back into scientific notation, right? So what she just supplied us with is the value of hydrogen at equilibrium. Cool? Let's read that question again, though, in case I just lost some people. You measure the pH of the solution, and it drops from neutral to an equilibrium pH of 1.98. This 1.98 is at equilibrium. Cool? So I was able to use your pH to figure out the H value at equilibrium. Now I know X, don't I? 0 plus X equals that. What can I do to all of the rest of the spots? I can put this is, what's this value here? The same thing, isn't it? And this one is 1.50 minus X. And we know the value for X because Reem told us. So this is going to be 1.49 something, something, something. But sig figs work out to 1.49. So we have calculated the molarity of hydrogen using the pH. And now what can I do now that I know all the equilibrium values? I can figure out my constant. It's what I'm constantly searching for. You might not have heard the groans at home or the sad laugh. The sad laugh of, please let this class be over. No. So we're solving for a constant. I can't do that in my head. It would be amazing if I could, but I'm just not that smart. You guys are writing stuff down, so I'll just 1.04 e to the minus 2 squared divided by 1.49. 7.26 times 10 to the minus 5th. Hey, Mr. Murphy. Yes, Matt. What are the units for K? Matt, there are no units for K. You can't see at home, but he's making furrow-eyebrowed face of confusion. Yeah, equilibrium constants vary so drastically from one equation to the last equation, to the first equation, to some of those weird equations, that the constants would be different units for every single equation. So as an entire group of chemists, we just decided to say, forget them. Let's just not write them down. Exactly. We literally just said, forget the units, move on. So you solve for the equilibrium constant, and then you walk away. That value there is a special type of K. Special K. Does anyone still eat special K? No. Yeah, I got one kid. What do you call this substance, H2SO4, that's giving off hydrogen? What do we call the substance that gives off hydrogen? I heard it. An acid. So this is a Ka. It's an equilibrium constant for an acid. We're going to spend a whole chapter on that. That's in the future. We're not going to deal with... This is a non-complex acid, but later on we'll deal with more complex acids. So, cool? All right. I did record all that, right? Okay, good. I just had this moment I thought I had paused and just never went over. All right, next page. Okay. The next example is something we are never doing. All right? It's totally doable. It's just not within the scope of this class. So let's just enjoy the problem and the fact that we don't have to do it. Okay, so let's just look at this question. So first of all, you don't have to write it down. You have been supplied with an equilibrium constant. Cool? You have been supplied with moles, moles. What's wrong with those two numbers? They're in moles and not molarity. And then you're supplied with a volume. So if you divide those moles by 2, you have the molarities. Bing, bing. It didn't give you any no, so the initial value of no is put as 0. Why is this value minus x? I have it, so I can take away from it. I have how much of the no? So I can only add to the no. So there's going to be more no when it's all done. So I'm going to add to this. So why is that 2x? Coefficient of 2. So what's very different about this question compared to the last two is now we've got this in terms of x, but there's no clue up here. There's no, at equilibrium, 12% is left. Or at equilibrium, there's now this mass. Or there's no clues. All you have is the constant. So you could write that. The constant equals the products squared divided by the reactants and solve for x. What type of math problem does that look like? For some of you, that's fun. For others of you, that's what you used to throw up in your mouth about in the middle of class. Oh, not one of those. I loved them. I'm not going to lie. That's the type of question I loved. It was a little bit of pain in a chem class, though. There's 4 different ways to solve that. One is a long, painful algebra process that everyone makes 7 mistakes on. Right? You're like, oh, I foiled it wrong. I got foiled by the foiling. Right? And you get to that negative b plus or minus the square root of 4ac all over 2a or something like that, whatever that was. Quadratic, right? The other method is your calculator will just solve those problems for you. You just carefully type it in and go, please tell me the answer. And 5 seconds later, it shoots out the answer. And I can show you how to do that if you want, but we're never doing it. Cool? Could this x could have 2 possibilities though, right? But in reality, the real world, there's only one possibility because the other one gives you a negative answer in your rice table. This one works. The other possible answer I think was 0.45. If you actually use the whole quadratic equation, why can't x be equal to 0.45? Right, you'd be 0.43 minus 0.45. I have a negative amount of oxygen left. I had to go into another universe to get oxygen. So this is not something we do. Cool? It's not something we do. However, if you look at that equilibrium constant, could you predict the value for x? That's a very small value. The x value is probably very small. It's not going to go very far before it reaches equilibrium because k is so small. This is the blank page. Le Chatelier is on part 2. I'm just going to come back here and stop for right now. You at home, feel free to watch part 2.